Good afternoon, students. We have seen the class A amplifiers working operation in detail in the previous classes. From today onwards, we will be going a little faster because we will be going with the next set of amplifiers or next types of amplifiers where there is not much of a much deeper analysis as that of class A. So why in class A itself we had such a large level analysis? The reason is class A has to provide completely faithful amplification and it is meant for audio amplifier circuits. Whereas the amplifiers which we are going to discuss from now on will not be utilized for audio applications. They are utilized for different other applications. So as such there is no requirement of a deeper analysis. Still we will have exercises with these types of amplifiers also. So as you see on the slide, you can see on the top you have one plus VCC and one minus VCC here. If you use one side NPN and one side PNP, that way we can have one half circuit and one more one half circuit, and load is shared by both of the half circuits. It is like in a bullock cart, if two bulls are used for drawing the cart. Now the two bulls will be sharing the actual load of the drawing of the cart or pulling of the cart. In that manner, this is the class B operation where you can see in the positive cycle one switch will be conducting and in the negative cycle another switch will be conducting. For example, in the positive cycle NPN will be conducting and in the negative cycle PNP will be conducting. That is why you are seeing here plus VCC and minus VCC that way, or minus VEE to be precise. This is one type of circuitry. Now if you don't want to use dual power supply there, we can have a slight variation in the circuitry where we can have only positive supply and ground. In that way we will have to have a biasing of both the circuit in such a way that in the positive cycle one switch will be working, in the negative cycle other switch will be working. So basically we will have two devices here who are working as switches. Switches in the sense in the amplifying operation only. And you can see at the upper diagram the load is connected to both of the switches, but in the lower side the load is connected in between with the capacitive coupling. That is because here we have a single supply and in general the output is supposed to be at half of VCC in the absence of the input signal. That is why I told you, if at all we employ the lower side diagram, then we will have to go for different type of biasing. We will see the examples in the class gradually. So this class B operation is provided when the transistor to be turned on when the AC signal is applied. Transistor to be turned on when the AC signal is applied. In the sense, only when the AC signal is applied, transistor will turn on. When the AC signal is not applied, it will not turn on. That is the idea here. I was discussing about the static power consumption in case of class A power amplifier. Such static power consumption will not be there in class B operation. That is because the switch will turn on only when the signal is applied. Otherwise the switch will be off. Either the upper switch or the lower switch, both will be off. Thus there is no DC bias and transistor conducts only for one half of input signal cycle, means either for the positive cycle or for the negative cycle respectively. The output can be obtained for complete full cycle with the push-pull circuit configuration as seen in the figure. Now this is called push-pull configuration. In the olden days we used to have push-pull trains. Even now also there may be push-pull trains in the hilly areas. The push-pull train's meaning is the train will have two engines, one at the front side and one at the back side. And we really cannot say which is front, which is back, because at both sides there will be engines. Two engines are provided in such a way. The reason is that in hilly areas and ghat sections, the train cannot take a turn again for going back through the route in which it came to the station. It requires an engine to be again brought to the front side and joined. Let us say the train went to a Darjeeling hill station, then if the train has to go back, then the engine which is at the front side has to be now connected to the back side, so to say. Back side will become front side now. But even moving of that engine would be risky in such cases, because there will not be such track available, or there would not be so much space available in the hilly areas. So the solution what they found was, let there be one engine inactive when the other engine is active. Means the front engine will be pulling the train as well as the back engine also. Now when it reaches the destination, let us say Darjeeling's hill area, now the back engine will become front engine. It will pull the engine at the other side. That will be off at that time. So that is how the name push-pull came into picture, because pushing and pulling. When one is pulling, actually it is pushing the other engine. That way. Pulling and pushing are together that way. That is how the push-pull operation came into usage. And the same terminology is used with the class B amplifier. In general, all class B amplifiers are push-pull amplifiers. That is because they have two switches. When one switch is on, the other switch is off. That way. Otherwise, there is nothing called pushing and pulling here. It is only a terminology used. The switch will be on, other switch will be off. That's all. So the same push-pull terminology which was used for the other applications, that was utilized here. Power transistors in the push-pull circuit deliver desired power to load and hence provide more efficiency than class A amplifiers. Now as you can see, there is no static power here. There is only dynamic power, which means normally if one is on, the other will be off. So only when the signal is applied, the device will turn on. Otherwise, both devices are off. So there is a substantial reduction in power consumption. So naturally, there is a higher efficiency in case of class B amplifiers operation. Let us see the efficiency calculation for class B power amplifier. Input DC power is VCC into 2 into IP by pi, because now it is working through AC. When it is working through AC, we are taking its value as 2 IP by pi. I hope you recall all these AC powers calculations which are already dealt with in the first year's courses. So DC equivalent of that AC is not actually average, it is twice the value of peak voltage divided by pi. Now you know that the DC equivalent is slightly different from RMS equivalent when it comes to the waveforms shapes. I will not get into all those electrical engineering basics, but this is now the input DC for class B. Whereas in class A, we were working with full cycle. You may ask that why in class B we are using this formula, whereas earlier we used Vp by root 2 or Ip by root 2. There the amplifier is working for the full cycle. When it is working for the full cycle, there we are comparing AC and DC with respect to driving the load. When it is driving the load, we always consider the RMS value, because the RMS value is the effective equivalent to the DC value while driving the load. But here in this case, there is no static power consumption. That is one thing. Second thing is, the amplifier is not working for full cycle. So when we calculate DC power, this is how we calculate VCC into 2IP by pi. That is the input DC power. Now the output AC power is P0 AC is VL squared PP by 8RL. Now this you already know. This is the output AC power. Load voltage peak to peak divided by 8RL when load is connected. At the input, there is no load that is applied. At the input, when one device is on, the other device is off. But at the output, always the load will be connected to the amplifier. Power will be shared by both of these switches per cycle. So output AC power's calculation is this way: VL squared of peak divided by 2RL. It can be VL squared peak to peak by 8RL or VL squared peak by 2RL. That root 2 gets squared and we have this 2RL. So now efficiency is P0 AC divided by PI DC into 100%. P0 AC is VL squared peak divided by 2RL, whole thing divided by VCC into 2 into IP divided by pi into 100%. So if we simplify this expression, we get peak value at the load divided by VCC into pi by 4 into 100%. You have to remember this expression now. Efficiency of the class B power amplifier is given in this manner: peak voltage at the load divided by VCC into pi by 4. When we multiply it by 100%, we get the efficiency in percentage. Now, when the peak voltage is equal to VCC, we are going to get the efficiency of 78.57%. That is why in the beginning of this module, when I showed you the tabular column, I had shown there that for class B power amplifier, maximum efficiency is 78.5% that can be derived mathematically. Now this is how it is derived. This derivation is important as far as the test and exam is concerned. Almost always this will be asked in the written test or in the theory exams. So it is simple as such. You will have to remember the DC power's expression, remember the AC power's expression, then AC power divided by DC power. You simplify this expression, you will get peak voltage at the load divided by VCC into pi by 4. Now whenever the peak voltage at the output is equal to VCC, then eta is going to become pi by 4 itself. Pi by 4 into 100% is 78.57%. That is how this is proved. So the maximum efficiency of a class B power amplifier is up to 78.5%, whereas in class A we had seen with the fixed bias amplifier we had seen it was about 25%, and later on with the transformer coupled amplifier we had seen up to 50%. Now with class B power amplifier it is up to 78.57%. Now what is the power dissipated by each transistor? Just a minute. Now to compute the power dissipated by the transistors, each transistor. Now both the transistors are not on. When one is on, the other is off. So if you have to calculate the power dissipated by each transistor, P2Q is PIDC minus P0 AC, because now the power is shared by two transistors. Q means quiescent power, because only when the input signal is present, the devices will be turning on, otherwise the devices will be off. So the total quiescent power is PIDC minus P0 AC, that is shared by both the transistors. So naturally PQ is P2Q by 2. So you will have to calculate input DC power, that is VCC into IP into 2 by pi, and you will have to calculate AC output power, that is Vp square divided by 2RL. Then you find out the efficiency, that is VLP peak by VCC into pi by 4. Now you know PIDC, you know P naught AC. The difference between them itself is the quiescent power that is dissipated by the transistors. Half of it is the power dissipated by each transistor. Let us have an exercise now based on the same formulae. A class B amplifier is providing a 20 volt peak signal to a 16 ohms load with the power supply of VCC 30 volts. Determine the input power, output power and circuit efficiency. Just a minute. Let me continue. Sorry for the interruption. There was an official call which I had to take. Okay. So class B amplifier is providing a 20 volts peak signal, means VP is 20 volts. Load is 16 ohms. Power supply is 30 volts. Determine the input power, output power and circuit efficiency. Now can the students note down these values? I will show you the previous slide with the formulae. I want you to work it out. Note down the output voltage peak is 20 volts. Load is 16 ohms. VCC 30 volts. Please note down. I want you to work out this and tell me the input power, output power and the circuit efficiency. I hope you have noted down. Let me go to the first slide now. I will show you the formula. Now find out the DC power. You have this VP which is 20 volts and you have this RL 16 ohms. You can easily find out IP. V by R 20 divided by 16 is the peak current. Peak current and VCC is given 30 volts. Peak current into 30 volts into 2 by pi, that is going to be the DC power. Similarly, you know the output VLP, that is nothing but 20 volts and you know RL 16 ohms. Apply this in that P naught AC, you will get the AC power. Now you can find out the efficiency. Find out the answer and put it in the chat box. I am waiting. Okay, Sayan is giving the answer. The efficiency is 52.33%. Let us see. Any other answers, students? Only Sayan has given the answer, others have not given. Anyway, let me show you the answer. Yes, it is correct, Sayan. Congrats. The peak current is 20 by 16, 1.25 amperes. So the DC current is 2 into 1.25 divided by pi, that is 0.796 amperes. PIDC is 30 into 0.796, VCC into that IDC, 23.88 watts. Now P0 AC is 20 square divided by 2 into 16. VLP square divided by 2 into RL, that is 12.5 watt. So the efficiency is 12.5 divided by 23.88, it is 52.35%. That is the efficiency. Similarly, you can calculate PIDC minus P0 AC, and that is going to be P2Q. DC power minus AC power is going to be P2Q. Half of it is the power dissipated by each transistor. Even though it is not asked here, now 23.88 minus 12.5 divided by 2 is going to be the power dissipated by each transistor. So this is how we can calculate the efficiency of class B power amplifier. You will have to remember all these formulae. You will have to work out and remember, that is the only way to remember safely. Coming to the maximum power considerations, where each device has to dissipate. Now the maximum output power is VCC square by 2RL. Why? The output voltage can be maximum up to VCC. So maximum AC power is VCC square by 2RL. And the maximum input power is what? Maximum input power is VCC into maximum of IDC. What can be the maximum of IDC? Maximum of IDC is again VCC by RL into 2 by pi. Because the voltage can be maximum up to VCC only. Beyond VCC, it does not make any sense. So now we are considering a single supply class B power amplifier only here, from ground to VCC. So it is VCC into maximum of IDC. IDC is nothing but maximum voltage itself can be VCC. VCC by RL into 2 by pi. That is 2 into VCC squared divided by pi RL now. Now, maximum power that is dissipated by the output transistor is the difference between these two, right? So that is P2Q is equal to PIDC minus P0 AC. This we have already seen. So that is maximum P2Q is, you can see the input power is 2 into VC square by pi RL, whereas output power is VCC square by 2RL. So now when we subtract them, we get this answer. Maximum P2Q is 2 into VC square divided by pi square RL. So that is how we get this PIDC minus P0 AC. You can perform this subtraction also, you can verify this answer. Now the power that is dissipated by each transistor will be this divided by 2, which means the maximum power which each transistor will dissipate is VCC square divided by pi square RL. That is P2Q divided by 2, that is VCC square divided by pi square RL. Why this is important? This is important because we have to select a device which can have at least double the rating of the maximum power rating. Now when we know the load resistance and when we know the supply voltage, we will be knowing the load resistance because we will be knowing to which particular load we connect this amplifier. And we will be knowing the supply voltage. Using those two, we can find out the maximum power dissipation by the transistors. Now based on this, we will have to select at least double the rating of this particular value in wattage. That is how we have to choose the devices. Otherwise, the life of the device is going to be drastically reduced when it cannot handle this power on a daily basis. Where do we use this push-pull amplifiers is in general wherever there is a pumping of current into the load where the shape of the waveform is not really very important. That is when we don't want to waste power in the case of audio amplification. For example, class A need not be used for a siren of an ambulance. Class B itself can be used where the signal shape is not really very important. Its output sound is important. So in many such applications where even though it is an audio application, it is not a speech amplifier. It is not meant for any music concert or it is not meant for any public function. So in all such applications where a heavy sound needs to be provided, for example, in the case of a siren in an industry or a factory, we don't have to go for class A amplifier. We can go for class B amplifier, where the amplifier will consume power only when the input signal is present. Otherwise, even if the amplifier is switched on, even if the power supply is given, it will not be consuming current because both the devices will be off. So that is how all these things become important about how to have a maximum rating of the device, how to choose the device. Okay, let me go to the next slide now. Now we have this phase splitter circuits. In the sense, if you have to use this class B amplifier, now for each device we will have to give that particular waveform itself, particular cycle, positive cycle or negative cycle, for which you require phase splitting. The complete 360-degree cycle should be divided into two cycles now, 180 degree and 180 degree, positive cycle and negative cycle. We will see how the phase splitter circuits can be utilized for this purpose. You can see this phase splitting with the center tapped transformer. Now, to the input, it is the normal input AC signal, but at the output, you will get two signals like that. One is out A, one is out B with respect to ground. Now, center tap of the transformer is ground. With respect to ground, when there is positive cycle there, at the upper terminal, you will get the positive cycle only, but the lower terminal, you will get the negative cycle because the coils are in the opposite direction there with respect to ground. The turns in the secondary of the transformer are in the opposite directions with respect to ground because ground is at the center tap. Due to which you will have two signals at the output of this transformer which are 180 degree out of phase. Now both of these can be utilized for driving those two switches. This is one phase splitting type. Now the phase splitting using the BJT itself. You can see when the input signal is there in the positive cycle, transistor will turn on, and you can see, you already know that when the transistor turns on, at the collector we will have 180 degree phase shift with respect to base. But what about the emitter? When the transistor is conducting, the waveform is available even at the emitter. In our earlier cases of voltage divider bias circuit, we had connected a bypass capacitor across this RE. Now instead, we will connect these two capacitors, one at the collector, one at the emitter. Now whenever we apply the input signal here, in general the transistor is kept in the active region, exactly in the middle of the load line. Now when we apply the signal here, simultaneously we will have both these signals available, one at the collector, one at the emitter. Now you can see these two signals are 180 degree out of phase. Now these two can be used for class B push-pull amplifier now, individually for each device. Now this is phase splitting using BJT. There is another phase splitting method using op-amp. Now this is the op-amp. In this particular circuit, we can see, just a minute. Okay, let me continue. You can see this circuit which is using the op amp now. Now there is an amplifier here. From the amplifier, we are giving additionally two amplifiers here. Now, input is given here. This particular amplifier, op amp itself is the amplifier. Using this particular amplifier, we are getting a 180-degree phase shift. Now that we can give to one more amplifier. Okay. I don't know why they have given the name EF. Later I will let you know about what is the full form of this EF. So in this EF now, you can see it is like a buffer amplifier now. So whatever is the input, that is available at the output. Now you can see for the other buffer amplifier, this is also op amp only. Op amp can be used as a unity gain amplifier. Unity gain amplifier is a buffer amplifier. Now the input is fed as it is. Now this buffer amplifier is not going to give any phase shift. Whereas for the upper case, we had another amplifier which was giving 180-degree phase shift. And because this upper amplifier is going to give a gain, we can have a potentiometer there just to adjust the amplitude at the both outputs. Because we want the same amplitude at the output of both buffer amplifiers. Because we are using it to drive one NPN and one PNP. Now this can be given to the push-pull circuit. So in this way, phase splitting can be generated using op amp also. So these are the three ways in which we can perform the phase splitting itself for the input signal. We had seen in the class A power amplifier that transformer coupling is going to increase our efficiency. Now, right now we had an exercise where we found the efficiency to be somewhere around 52%. But the maximum efficiency that is possible with the class B amplifier is 78.5%, as you already know. Now, if you do a transformer coupling with this class B push-pull, then the efficiency can be further increased. That we had seen with the class A also. Let us see that now in class B. You can see now, this is that class B push-pull amplifier, complete amplifier now. There is a phase splitting transformer. We had seen in the previous slide how phase splitting can be performed using a center tapped transformer. That is there now here. And then we have a push-pull circuit connection. At the top you have NPN, at the bottom you have one more NPN. And at the output you can see another transformer which is connected to the speaker. Now this can be a circuit inside the siren of an ambulance or inside the siren of a factory or industry, where input AC will be given from an oscillator. You have already studied the oscillator now. Let us say for a siren, 1 kilohertz signal is required. Now that 1 kilohertz signal, let us say in an industry or a factory where the morning bell will be there for the morning attendance and even evening bell will be there for the closure of the work. So they can have a 1 kilohertz oscillator there. 1 kilohertz RC phase shift oscillator or a VN bridge oscillator, because that is meant for audio applications. Now you can have a oscillator here. Let me write an oscillator here now. There can be an oscillator here now, connected like this. Let me write it clearly. This is the symbol for oscillator. So there is an oscillator here that is going to give an AC signal. Now because of this center tapped transformer, you can see these dots. The dots indicate the commencement of the turns that way. Now always the turns will be wound in this manner, winding will be in this manner. Now when we take a center tap at the middle, automatically you can see upper side winding it has started here and the lower side of the winding is starting here. Naturally these two will be having opposite inductions. Now why is this R1 and R2? The R1 and R2 is provided as a biasing resistor for the transistors. You can see R1 and R2 is connected to the base by means of this inductors coil only. Even though it's a transformer, at the output you can see there are two inductors. And from this point it is going this way to the base. From this point it is going to the base here. Now we have to keep this transistor in the middle region, right? We have to keep the transistors in the middle of the load line or in the mid active region. So we require some biasing current here. So in this case you can see that there will be some static power consumption also even when input signal is not there. Circuit to circuit it can be different. In the case of class B operation there can be multiple designs this way. So there is a partial DC current, but DC current can be ignored because it is only a base current. At the output you will not see VCC at all. Just look at the circuit. At the output there is no VCC at all. There is no output DC as such. Only at the input you have this VCC. So to some extent base current will flow to keep the transistor in the active region. Now when the oscillator's input is supplied to the transformer, positive cycle will appear here. At the same time the negative cycle will appear here. When the positive cycle is appearing at the upper winding, Q1 will turn on. At that time Q2 will be off, because when the positive cycle is appearing here, it is the negative cycle appearing here. So when Q1 is on, Q2 is off. When Q1 is on, VCC is connected to the middle of this center tap at the output. Okay. So this is going to conduct this way. Anyhow that arrow mark is there. Q1 is going to conduct at that time. But at that time the winding at the lower side will not be working as such because Q2 is off. Now when it comes to the negative cycle, Q1 will turn off, Q2 will turn on, and the current will flow in this manner now. Current will flow later on when Q2 is turning on in this manner. I think I should change the color of this. So when Q2 turns on, there will be a winding across N1. So accordingly, Q1 will be on, Q2 will be off, or Q1 will be off, Q2 will be on. So there is this push-pull operation, and because of the supply connected at the middle of the center tap transformer at the output. Now accordingly AC will be induced at the secondary of the output transformer, and that is connected to the speaker. As I told you earlier, to the speaker there is no DC current flowing at all. You can see this VCC is utilized only for biasing of the circuit as such or the BJT as such. Otherwise, for the load there is no static power consumption at all because it is transformer coupled. In this manner efficiency can be increased. You have a phase splitting input transformer here, then you have a push-pull circuit connection, then you have a push-pull output transformer, finally you have the loudspeaker as the load. This is the transformer coupled push-pull amplifier. During the first half cycle, Q1 conducts, and during the second half cycle, Q2 conducts. Therefore, overall signal developed at the output varies over the full cycle of operation. We have seen the basic push-pull circuit till now. There are some varieties of push-pull circuits. Let me show you. These are called complementary push-pull circuits. Now this is one circuit. Here you can see there is no base current at all for this circuit. At the base you will not have any resistance at all. You will not have any biasing, unlike the earlier circuit I showed you. So when the input signal is applied, in the positive cycle the upper transistor will conduct. Okay. In the negative cycle the lower transistor will conduct. You can see the lower transistor is a PNP. upper transistors in NPN, and you can see that VCC around NPN, and you can see this VCC2 around PNP. We can call it as VEE actually. The lower one can be called as VEE because it is connected to the emitter here. So in the positive cycle NPN conducts, in the negative cycle PNP conducts. In the absence of the signal, nothing conducts. Now the load can be connected in between the emitters and the ground here. Now this point is the ground. Let me annotate. Now this is ground. With respect to ground, when upper one is conducting, it is conducting this way, and lower one is conducting this way. Now due to which you can see that when the input signals, two cycles are there, two transistors are conducting, and across the load respectively the current direction also different. You can see this in the upper transistor. Upper transistor, the direction of current is in this manner. In the lower transistor, the direction of current is in the opposite manner. So that way across the load, output AC is induced. Now you may think outside we have, at the output we have DC, right? At the input we have AC. But using DC only, AC is produced by means of this push-pull operation. So in this manner also, we can have a class B push-pull amplifier. Now you can see the waveforms there. When the input is having a complete 360-degree cycle, at the output there is a crossover distortion. What is the meaning of crossover distortion? When the input signal is reaching up to 0.7, NPN is off and PNP is also off. Both are off. NPN will conduct only when the input signal goes above 0.7, and PNP will conduct only when the input signal comes below 0.7. Because in the case of PNP, current goes out of the base. In the case of NPN, current goes into the base. So, when positive cycle exceeds 0.7, then only NPN conducts. When the negative cycle exceeds minus 0.7, then only PNP conducts. In between, both are off. When in between both are off, you can see here, across the load, there is nothing there. Across the load, there is no signal there. Now that is called crossover distortion. In this particular arrangement, we will have to compromise with this distortion now. Even though it's a distortion, we will have to compromise now, because we are trying to save the circuitry. We are going to have higher efficiency. In that case, even if the crossover distortion is there, it does not matter for us, because we are not using it for a regular speech amplifier. That is the idea here. There are methods to overcome the crossover distortion also, that I will show you later on, maybe in the next class, not today. So you can see here, using NPN and PNP transistors, it is possible to obtain a full cycle output across the load. Only thing is, NPN is on during positive half cycle and PNP is on during negative half cycle. Both are off during zero crossover. Therefore, disadvantage of this configuration is the crossover distortion. But the advantage is, there is no static power consumption at all. Absolutely it is zero, because both are fully off. Unlike the previous circuit where I showed you two resistors R1 and R2, they were used to bias both those transistors. There we had both NPN. Here we have NPN and PNP, because of which we need not bother about biasing them. Input signal, it will drive both of them. Now you may think, if the input signal is given to the transistors, if they conduct, how we can have an amplification, right? The amplification is happening because of the value of VCC. You can choose the value of VCC as 30 volts, 40 volts, 50 volts, 60 volts, even 100 volts. Based on the value of this supply voltage, we can have a much